Let's begin to talk about one-to-one functions and inverse functions. So what I have here is a function. Remember, a function is a relation, and a relation is a set with an ordered pair in it, at least one ordered pair. Here I have 3. Now, with these ordered pairs, if you look at the first numbers, they are different. And the fact that they are different, that would mean that the relation is a function. So this is a function. However, if you look at the first and the last ordered pair, those two, the first numbers are different, but the second numbers are the same, namely 4 and 4. So this is a function that we say it is not one-to-one. Therefore, if we add another restriction, an additional restriction, so that now the function has different second components, then the function becomes a one-to-one function. So for instance, I could have, I'm going to keep the 3, but I'm going to change 4 to 5 here. So this is a function now. First number is different, and so are the second numbers are all different. So this is a function that is what we call one-to-one. Now the notation for one-to-one, we put 1-1. These are numbers 1. Don't do 1 minus 1 equals 0. We're not doing operation here. It's just a notation. So that's what a one-to-one function is. Now formally, we can say a function is one-to-one in general when for two different x's, we get two different y values. You see that? That's exactly what I have in the relation up here. Anytime x1, x2 are different, so are the y values, f at x1, x2. Now, if we have the graph, by the way, what would this imply on the graph of a function? So let's say I have a function here. I have a parabola. It is a function. If we do a horizontal line anywhere on the graph, right? It could be anywhere. But if I do a horizontal line, and if the horizontal line crosses the graph of the function at 2 or more points, then that is indicative that the 2 points are collinear because they fall on the same straight line, right? These 2 points are collinear. Therefore, they have the same y value. So here's a case where x1, x2, two different x's, but the y's are the same. F at x1 is equal to f at x2, same ordinate or height of the graph. Therefore, f is not one-to-one. Now, the importance of one-to-one function is, we'll see that in a few moments here. It's very important for the functions that we work with to be one-to-one. So this way we can establish a two-way communication between input and outputs. So right now with a function, you have a one-way direction. And then later when we talk about the inverse function in this video, we talk about the inverse function, then that's something, an ideal property of functions that we would like to have. Okay, so there you have it. Now, thinking about, for example, let's go back to our library of functions. Remember in our library of functions earlier, we had, I think, 7 or 8 functions we talked about earlier. So if I look at, for instance, the linear function in this form, not a horizontal line, and a vertical line is not a function, fails the vertical line test. But the horizontal line that's oriented like this, notice it passes the horizontal line test. Okay, and in fact, that's what this horizontal line is. We often refer to this as the horizontal line test. It's simply a visual test to determine if the function is one-to-one or not. So the linear function, this is one-to-one. Okay, and then the parabola we just showed is not one-to-one. Let's say I have the absolute value function, this one. Well, this too fails on so many levels, the horizontal line test. So this one is not one-to-one. The absolute value is not. We talked about the square root function, for instance, right? the square root function, that one. Well, the square root function passes the horizontal line test. So this function is indeed 1-to-1. Okay, so for any of them, as long as we have the visual, the graph, we can determine whether it's 1-to-1 or not rather quickly. So the basic cube function is 1-to-1. So some of these are, others aren't, and just that's how the way it is. Now, in terms of increasing or decreasing function, if a function is increasing like this one, it will pass the horizontal line test, right? Therefore, increasing functions are 1-to-1. So this function is increasing, and it is 1-1. It is 1-to-1. So are decreasing functions. So if we look at decreasing functions, they too pass the horizontal line test. So this function is also 1-to-1, only it's decreasing. So it's decreasing and 1-to-1. All right. Now, so enough about 1-to-1 functions. Let's talk about inverse functions now. Inverse function. If a function is 1-to-1, then its inverse exists. If a function is 1-1, 1-to-1, the inverse of that function exists. Inverse exists. So the question is, how do we define this inverse function? Now, notationally, by the way, remember we use f of x for the function. That's the function, right? And we use the superscript -1 of x for the inverse function. Now you got to be careful with this notation, by the way, the superscript. Notice I could refer to it as a superscript. I didn't say that's f to -1 power. In this work with inverses, when we talk about f inverse of x, that does not mean 1 over f of x. We are not talking about the negative exponent, okay? This is simply a superscript. That's all that is, a superscript. It doesn't have a numerical value attached to it. So how are we going to find the inverse of a function? Let's take a look at that. Let's say I have, in this example, suppose I have a relation that is a function that is 1-to-1. We'll make this simple. 1, 3, 2, 4, and 7 and 11. Okay, so suppose that is a function. First number is different, second numbers are different also. The domain of this function, the domain of f, or the set of all first numbers, so it's going to be 1, 2, 7, and the range of this function is going to be the set of all second numbers, 3, 4, and 11. Okay, now here's how the inverse function is defined. The inverse function is a function that you obtain, and I'm just going to use my superscript -1 to show that. It's a function that you get by switching or swapping the x and the y components of the function, the original function, that is. So 1, 3, when you switch or swap, you're going to get 3, 1. 2, 4 becomes 4, 2. And 7, 11 becomes 11, 7. Okay, and that's all the inverse function is. What's important is that swap or switch that we do between the elements of range and domain. Now, because of this swapping, by the way, look at the domain of the inverse function now. No surprise, it's going to be exactly the same as the range of the function. So it's going to be the same as the range of the function. And I'm using funny looking R for the range. And what about the range of the inverse? Well, it's going to be exactly the same as the domain of the function. These are the range values. Okay, now this we're going to make a note of, and we're going to actually do this throughout our work. Anytime the question asks, or if we want to find the range and domain of the inverse, we often go back to the original function before it was swapped out and determine those from the original function. It's a lot easier to do it that way. Okay, so how is this gonna look like in terms of our mapping? So let's say I have the mapping of the elements. Suppose I have x and y here. The mapping takes place through function f. Okay, and here we have y as a function of x, right? Because you start with x, you end up with y. Now we can actually go back from y to x. So we initiate a move from here. So y becomes the input actually this time, and x becomes the output with respect to the inverse function. You see that? Therefore, we can say that through the inverse, remember the input is y. So that means f inverse, input is y, output is x. And that's what that means. All right. And there we have them. So that's the connection between the function and its inverse. Now, something interesting about the function and its inverse is if you do the composition of f inverse of f of x, the outcome is going to be x. Okay. And this follows from what I have here actually, f inverse y, but then y is f of x. So if you plug in f of x in here, that composition should be x. All right, and let me erase it on this one. So this is something important. And also, not only that, but if you do evaluate at f inverse of x, that composition will also give you x. Okay, now it's important for these to occur. For example, for this one, x should be in the domain of f. And here, x is in the domain of f. And for this one to work, the bottom one, for this one, x must be in the domain of the inverse. Now, another way we could also mention this. Remember, domain and range of a function and its inverse. When we say x is in domain of f, is the same thing as saying x is in the range of the inverse. For this one, when we say x is in the domain of the inverse, that's the same as saying x is in the range of the inverse. So often we use those interchangeably. And okay, so we did talk about this important composition between the function and its inverse. So let's do an example right off the bat here. Suppose I have f of x is x cubed minus 8, and I'm going to make g of x to be cube root of x plus 8. All right, and we want to just verify that these two functions are inverses of each other. Now, if I look at the domain of the function, by the way, polynomial function, all real numbers, and the domain of g, it's cube root. Remember, if the index is odd, that's 3, 5, 7, and so on, then there is no restriction on the radicand. Only even indices like square root, fourth root, radicand must be positive. So both of these have domains that are negative infinity to infinity. So the composition is going to work for any value of x in this case, because of both of these domains being all real numbers. So let's do f of g of x. Now f of g of x, that's when I do f evaluated at g of x, which is cube root of x plus 8. Okay, and then I'm just going to plug in into the polynomial function a cube root of x plus 8. True, and then f will cube that, subtract 8 from it. Well, cube root of anything cubed, you just get the radicand back. And you can see clearly the composition is x, okay, which is the identity function. Now, if I do the composition of g of f of x, For this one, I do g evaluated at f of x is x cubed minus 8. True. It's up here, x cubed minus 8. And this time we're going to plug into g. Well, g will take cube root of the input, and the input is x cubed minus 8. And then it adds 8 to it before it takes the cube root. So it adds 8 to the input and then takes the cube root. That's going to be cube root of x cubed, and no need for absolute value here. With again, cube root, fifth roots, and so on, we don't need absolute value because x could be positive or negative. And there we have it. So we did confirm that the composition in both directions give you the identity function. Okay. Now the fact that you get the identity function when you change the order of composition translates into something interesting in terms of the graph of a function and its inverse. So let's take a look at this next example. Okay, so suppose I make up a function x cubed minus 1. Okay, now for this function, let's find the domain of the function because it's polynomial, negative infinity to infinity. Okay. And let's do the range of the function. The range of the function is also negative infinity to infinity because it's a power function shifted down 1 unit. We'll graph this in just a moment. So we got that the information for that. Now, without knowing anything about the inverse, this is so cool. About the inverse, haven't even done anything about it. We know that this would be the range of the inverse and that this will be the domain of the inverse. Alright, so now let's actually graph this function. Okay, so what I have here are the coordinate system, or is the coordinate system, and what I have on that coordinate system, this line that you see, actually I should make that a dotted line. And this is the line y equal x. Okay. Now, the graph of x cubed minus 1. If you recall, that's going to be a power function x cubed. And remember, our power function x cubed look like that. Minus 1 is when you drop it 1 unit below the x-axis. So it's going to look something like this. Okay, that's that portion of the graph. So this is the graph of f. Now the graph of the inverse is going to be symmetric with respect to the y equal x. Now the point that crosses the on the function, the point on the graph of the function that crosses y equal x will be exactly the same as on the graph of the inverse. But let's say this point, whatever this point is right in here, that point is going to reflect over here about this line. Okay, so it's going to end up in here. And this point, for instance, that is on the y-axis, is going to be now a point on the x-axis. Let's see how that works. So if I do a reflection, then the reflection is going to look like this. There, and that will be the graph of the inverse. That, and right there. Okay, now my line, actually, if it was exactly 45 degrees, let me adjust it and make it a dotted line in a moment. And there it is. So I did make a dotted line and I adjusted it to where we can see more of a symmetry. This portion of the graph is the same as this one, and this portion will be the same as this part. Okay, so here's a graph of the inverse without again going through and finding the equation of the inverse. If you want to find the equation of inverse, by the way, we could, and remember to do that, we're going to swap x and y. So we're simply going to switch them. Okay, the function y is x cubed minus 1, right? This is what f was. We want to find the f inverse. F inverse is when we switch the x and the y and then we solve. So it's a two-step process: a switch or swap and solve. And then we're going to solve for y. Okay, so how do we solve for y here? Add 1 to both sides. And then from here, if we take the cube root of both sides, we get cube root of x plus 1. And at this point, we call that the inverse function. So that is actually the equation of this blue curve that you're seeing. This is given by, I'm just going to put the equation there, cube root of x plus 1, which is a cube root function. Remember, our cube root functions look like this. Plus 1 shifts it to the left 1 unit, and it's going to look like so, right? And that's exactly what that is. But we only use reflection to do that. All right, very again useful information that we have here. This point, by the way, is when x is 1, y is 0 on x cubed minus 1. That means this point, by switching, I get 0, 1 on the graph of the inverse. This point was the y-intercept of the cubic function. This one, when x is 0, y is negative 1. That means you swap it, you get negative 1 comma 0 as the coordinates of the x-intercept here. Alrighty, so we have that one. Let's take a look at another example here. So for this next example, suppose f of x is given by x squared plus 4. And this time I'm going to make x positive, because if you remember x squared plus 4, that will be a parabola that is shifted down, right? 1, 2, 3, 4 units. So it's going to be a parabola that looks like this, right? Well, the parabola is not 1-to-1, correct? So to force it into a 1-to-1 function, I'm choosing to go with simply the positive right there, the positive branch of that parabola. And so this is actually negative 4 here, there's 0. And here's my function. And this would be the domain, by the way. I've already given you the domain of the function. What is the range of the function? The range of the function is from negative 4 to infinity. That's where the graph starts, and it goes all the way up. So on the y-axis, you see that it projects to the y-axis like so. And let's see. So those are the things we wanted: domain, range, and the graph. Now let's actually graph this against this line, y equal x. Again, all functions and their inverses will be symmetric with respect to that line. So we can immediately get a couple of points here. And by the way, the x-intercept here is going to be, let's see, we have x squared plus 4. So for this one, the x-intercept, that's when you set y equal to 0. Oh, actually, this is x squared plus 4. So sorry, I know you guys caught it, I didn't. So I actually need to move this up, correct? I need to move the parabola up 4 units, not down 4. It's plus 4. 1, 2, 3, 4. So there you go. This is what the parabola looks like. We still want the right branch of that. So this point is actually 4. All right. Now the point that is on the y-axis is going to end up on the x-axis. So it's going to be 1, 2, 3, 4 here. And then using reflection about this line, I'm going to draw it like so. There, that's what it's going to look like. And my line is not quite 45-degree angle line. There it is. Because these distances need to be the same distances. All right, it looks much better now. And indeed, we're looking at the graph of the inverse f, that's f inverse, only through reflection. Okay, and let me fix this one. The range of this function is from 4, not negative 4, 4 to infinity. All right, and And there you have it. So what are the range and domain of the inverse? Well, domain of the inverse is going to be that. If domain of the function was given to be from 0 to infinity, that means that would be the range of the inverse. The range of the inverse is from 0 to infinity. Remember, range is, or these are the y values. So everything looks fine on this one. If I want to find the equation of the inverse, again, the function f is y equal x squared plus 4. So we're going to swap x and y. This becomes x equals y squared plus 4. And then solve. Two-step, right? Swap and solve. We're going to solve for y. So to solve for y now, subtract 4 and take the square root. So we get y is equal to plus or minus root x minus 4. Now because the domain of the inverse function is right in here. The domain of the inverse function is from 4 to infinity. And what about the range? Oh, the range actually. The range is 0 to infinity, so that means positive, correct? And when we think of range, we're thinking about y values positive in this case, because 0 to infinity. Well, to get positive range here, we're going to throw away the negative sign and keep the positive in front of the square root. Therefore, the inverse function is given by square root of x minus 4. So that's got to be square root function, the basic one. Let's move to the right 4 units. And there we have the graph of the inverse as well as the equation of the inverse. Okay, now let's take a look at another example. In this next example, suppose I have my f of x is equal to 2x over 3x minus 1. All right, and we do want to find the domain and range and also as well as the equation of the inverse, but we don't need to graph these. So let's begin with domain of the function. Domain of a rational function is all x except what makes the bottom 0, right? And so we know that it's going to be x, so that x cannot be 1/3. Because 1/3 makes the denominator 0. You see that? At 1/3. So it cannot be. We want to prevent division by 0. All right. And so this becomes the range of the inverse now, doesn't it? Domain of f. But let me just refer to that as the range of inverse also. That's the range of the inverse. Cool. So we got that part. Now let me remove this portion. All right. Now what about the range? Let's hold off on the range of the function. Usually range it may be easier because range of function and domain of the inverse will be the same, right? So I'm hoping I can it'll be easier for me to get that range of the function bouncing off of the domain of the inverse. Now, let's find the inverse. We're going to swap the x and the y. So x is equal to 2y over 3y minus 1. See up here? F of x and y are the same thing. So that's why I just called it y down here. Now to solve this, let's cross multiply them. We get 2y is equal to 3xy minus x. And then let's bring 3xy, or let's do this. Let's keep 3xy on this side. Move 2y to the right and shift x to the left. And there you go. So I don't have to manipulate the signs this way. And then we're going to factor the y. So that's going to give me 3x minus 2. Okay, factor in the y. And let's see. It's 3y. Yeah, so it gives me 3x minus 2. And then divide both sides by parentheses. So from here, we get y which is f inverse of x, is equal to x divided by 3x minus 2. And there we have the equation of the inverse. Now from this, we know the domain of the function inverse, again, will be places where the denominator cannot be 0, so x cannot be 2/3. That's what makes the denominator 0. You can set it equal to 0 and solve for x to see for yourself. See, now I can actually do the range of the function. So that is the range of the function, right? Except for the range of the function, let's see, we look at y values, correct? So let me rewrite it. All right, let me do it this way. So domain of the inverse, again, anything but 2/3, right? So that means on the range of the function, therefore y cannot be 2/3. This is true, but remember, because see, for domain we use x, for range we use y. That's why. So the range of the function here is going to be y, such that y cannot be 2/3. And one thing we could do, by the way, here also, if you look at the rational function, remember we had a theorem on horizontal asymptotes. The horizontal asymptote of the graph of this function is 2/3. So that means the function will approach it for a very large x, a very small x. So the question is, will 2x over 3x minus 1 cross 2/3, which is the y value for the horizontal asymptote, and this is the y of f. We did this kind of work in previous chapter. So if I do this, I get 3 times to cross multiply. We get 6x is equal to 6x minus 1, 0 equal -1, doesn't equal. So f does not cross the horizontal asymptote. The f does not cross its horizontal asymptote. Well, if it doesn't cross, then that means it's not included, right? We can get that right off of this one. All right. Now, therefore, let me adjust my range of the inverse function. So the domain of the inverse function, what was that? The range of the inverse function, therefore, is going to be y, such that y cannot equal to 1/3. Okay, and again, we can test whether this crosses the horizontal. It won't cross it. So got to be careful here again on how we label these. All right, so we got the domain and range. Now let's show that f of f inverse of x is x. Now, so that means f evaluated at the inverse. The inverse, I have it in here. That would be x over 3x minus 2. All right, that's what the inverse is. Now we're going to plug this into our f function. The f function is the original 2x over 3x minus 1, that one. Okay, 2x over 3x minus 1. So the input, which is x over this input right here, x over 3x minus 2, is going to be replaced by x in the function. So that's going to be 2 times x over 3x minus 2, and then divided by 3 times x, but then the red expression, 3x minus 2, that would act as an x, this x, and minus 1. All right, so this is what f of x was. Now let's work this fraction. And this is a complex fraction. The easiest way to get rid of fractions within fractions, think of it like that. Not within, but you know what I mean. When we have fractions, top and the bottom are secondary fractions. The easiest way to eliminate them is to multiply by the LCD, which is 3x minus 2 times 3x minus 2. So in the numerator, we're just going to get 2x, right? Because these cross out. In the denominator, we're going to distribute 3x minus 2 to both expressions. Again, 3x minus 2 and 3x minus 2, those cross out. Okay? But since I'm going to distribute it to a negative 1 also, I'm not going to cross them out like I did the one above. As a result, the first term is going to be 3x minus, and then 3x minus 2 times negative 1 would be 3x minus 2. Okay. And what else do we need? And we need to, hold on. Well, let's do the following. I'm going to remove the arrows here. Okay, let's simplify this one. Now 3x minus 3x, those cross out. Negative negative is positive 2, so this is 2x over 2, which is x. And there we just showed the composition is x. So that means our inverse function is the correct function. We found it correctly. Let's verify the other composition. This time the composition of f inverse evaluated at f of x. And remember, f of x was 2x over 3x minus 1. All right, so I'm going to use that. 2x over 3x minus 1. Divide by 3x minus 1. We're going to plug this into our inverse function. The inverse function is x over 3x minus 2. This is the x over 3x minus 2. There you go. Now let's work this fraction. This 2, we're going to multiply top bottom by the LCD, which is 3x minus 1 times 3x minus 1, and let's see what happens. In the numerator, we just have 2x. In the denominator, what do we have? 3x minus 1, 3x minus 1 cancels, and 3 by 2, so I have 6x minus twice 3x minus 1. Distribution to 2. This distribution onto 2. And then let's remove parentheses in the bottom. So we get 6x negative 6x plus 2. 6x is cross. I mean, not cross, they add to 0. The 2's crossed now. And we get x. So the composition in both directions, we gave us x. As a result, we verified that this is the correct combination. I mean, the correct composition, not combination. All right, now let's take a look at our last example. This example again, let's work at rational expression. Usually these are a little problematic because they involve complex fractions. And you know what I mean by complex fraction, right? Like a over b, c over d. This is a complex fraction. A over b over k, that's a complex fraction. 2/3 over 1/2, that's complex. Doesn't mean it's complicated, it's just a fraction over a fraction. Just the terminology for that. Okay, so for this one now, let's say you are given x is greater than 0 so that the function is 1 to 1. Okay, this is an even function, by the way, just to note that, because you have x squared here. Change x with negative x, doesn't change it. You get the original function back. All right, so we already know the domain of this function is given. It's going to be x greater than 0, which means 0 to infinity, right? Now, let's find the inverse. F inverse of x. That's when we switch x and y, right? So we got to do our swap step. So therefore, y equal the original over 2x squared. This one turns into x equals y squared minus 4 divided by 2y squared. Cross them and we get 2xy squared is equal to y squared minus 4. Okay, now we want to solve for y, correct? So I'm gonna keep the y squared on the right side, move 2xy squared to the right, the sign changes. Bring -4 to the left, the sign on that changes. I'm then going to factor the y squared. That gives me 1 minus 2x. Therefore, y squared is 1 minus 2x divided by 4. So we can take the square root, and the square root is going to give me plus or minus 1 minus 2x. Sorry, I didn't do that right. You divide 4 by 1 minus 2x. Okay, so this is going to give me 2 divided by square root of 1 minus 2x, right? Now, domain of the function is 0 to infinity. That means the range of the function, inverse function, is 0 to infinity. If the range is 0 to infinity, that means the y values are positive, correct? Well, if the y values are positive, we're going to discard the negative of y. So we're going to choose y equal 2 divided by square root of 1 minus 2x as our inverse function. I'm going to use the inverse notation at that point. So here is that. So we got our inverse function. Now what is the domain of this one, by the way? The domain of this function, domain of the inverse. Not only we cannot divide by 0, but remember we have to look at the implied domain of the square root. So that means 1 minus 2x has to be positive. Add 2x to both sides, divide by 2. So x must be less than a half, right? X must be less than 1/2. That means -infinity to 1/2, not including a half. All right. And we have that domain of the inverse. We can write it in set builder notation, like so also. Either interval or set builder notation. Now the domain of inverse function here is going to be exactly the same as the range of the function. So for this one, the range of f is going to be from -infinity to 1/2. It's much easier to swap out these range and domains when they are in interval notation as opposed to when they are written using x, because if we use x, then we end up with what we have up here. You see that? That's how we got to do this. That's because we kept the set builder notation. We could have done the same thing using interval notation up here, by the way, as well. But now I have it down here for your reference. Okay. So we did all that we needed to do here. Range of f, domain of the inverse, we have that. Now let's show the composition as one. Okay, first I'm gonna do f of f inverse of x. That would be f, the function evaluated at, the f inverse is here, 2 over the square root 1 minus 2x. And with this, we need to plug in that fraction into function f. Remember, function f was x squared minus 4 over 2x squared. So that's what I'm going to go replace it. The numerator was x squared minus 4. Here's the x squared minus 4. The denominator was just 2x squared. So we're just going to do 2, and then x is 2 over, let me use my red color, 2 over square root of 1 minus 2x, and then we square it. Okay, just real quick, this is what I plugged into. Now let's simplify this. When we square the in the numerator, when we square this expression, the numerator is going to be what? It's going to be 4. Denominator is going to be just 1 minus 2x. We're going to lose the radical, minus 4. Divided by, in the denominator, we're going to have 2, and then 2 squared is 4. That gives me 8, right? 8 divided by 1 minus 2x. Square root of that squared, which gives you just 1 minus 2x. All right. Now, I'm going to multiply the top and bottom by the LCD. The LCD is 1 minus 2x, the binomial in the denominator of both the top and the bottom fractions. So now when I distribute, 1 minus 2x cancels, so I have 4 minus. And then the second distribution is this one. 1 minus 2x times 4 makes negative 4 plus 8x. You have a pair of opposites. They add to 0. In the denominator, the binomials just cancel. So you get 8x over x, and that's just x. So we showed that composition is just x. Now let's do our last composition, and we are done. Or we will be done. All right, for this one now, the inverse function. We're plugging into the inverse function again, this one. All right. 2 over square root of 1 minus 2x. This is the inverse function, right? This is where we're plugging into. What are we plugging in? We're plugging in f of x. And remember what f of x was. F of x, x squared minus 4 over 2x squared. Okay, just for now, and then I'll erase this in a moment. And therefore, we are plugging into the outside function. The outside function is the square root. That means I'm going to do 2 over the square root of 1 minus 2x, but then x is now f of x, which is 2 times x squared minus 4 divided by 2x squared. Right? That's what we just did. All right. And then I don't need these references anymore. Now we can do the algebra real quick, and then we will be done. So what is this going to become? The numerator is just 2, and the denominator now. 2 in front of the fraction, the 2 in the fraction, and the denominator cancel. So that's going to make this square root of 1 minus x squared minus 4 divided by x squared. Okay. And then let's combine the two fractions in the denominator. That's going to be x squared minus 4. The LCD is x squared. See the 1 here? Write it as x squared over x squared minus the fraction next to it. And that's how I got this numerator. All right. The x squares are opposite. They add to 0. Now I have 2 divided by square root of. Oh, and I'm subtracting, so this is positive, right? Because I have negative of negative 4 makes positive 4. And so this is just going to give me, what, 4 over x squared, which we can take the square root of 4. It's going to be 2 square root of x squared is going to be absolute value of x. Invert and multiply 2 times absolute value of x over 2. And that's just absolute value of x. Now, it is absolute value of x, but then absolute value of x is x if x is positive, and it's negative of x if x is negative, right? And in our case, look here. We were told x is positive, right? And because we're doing this composition, f inverse of f of x, we look at the domain of the inside function, which is x positive. So this is simply x. We don't need absolute value. All right, and that should be it. So we were able to do a lot with one-to-one functions and inverse functions. Very useful. Now, again, what we've done here works for all one-to-one functions and their inverses. In our feature section now, we're going to we're going to take that and we're going to join them in with our transcendental functions, exponential, and then logarithmic functions, which we're going to be talking about next. We're done with this one. As always, thank you for watching.